Okay, let me skip a little bit, and then now just one thing is I have to mention that the dimension now come down to dimension 2 and 3, and, using the general theory. But dimension 2 is well known. I mean, yeah, because dimension 2 and compact is orientable then only surface. Compact surface of genus G is 0, 1, genus G. So then, two-dimensional affine case.
너무 가까이는 안 되는 것 같아요. 그 정도로 네, I mean, it's focus.
Okay. Here is a fact. Compact. First, the Riemannian. Compact Riemannian manifold. Gamma. Riemannian fract. Then this is yeah. This point is because in the dimension 2, so everything is crushed by genus G. That's it, diffeomorphic. But in like affine flat or Riemannian flat case, the statement is compact Riemannian flat manifold is affinely diffeomorphic to either torus or crime bottom. No, crime bottom. This actually, let me mention one thing. Suppose you have T2 and crime bottom has anyway Riemannian flat structure. So this is a Riemannian flat manifold. And you have a complete Riemannian flat manifold gamma. This and this is fundamental group is isomorphic. Then they are affinely diffeomorphic. This is obtained by Weaver buffer GT solving. So in this case, any compact Riemannian flat manifold is affinely diffeomorphic to one of torus or crime bottom. They are of course diffeomorphic, but affinely. Next is then the compact. Next is a compact. Let's say Lorentz flat manifold. How to is this also affinely diffeomorphic. Affinely diffeomorphic to again torus or crime bottom. So there is a Lorentz structure on torus also K, and then the two further the group is isomorphic. Then they are in this case also affinely diffeomorphic. I didn't mention that Lorentz flat case is like notation is like this. Expression and semi-direct product with O1 n minus 1. Okay. O1 n minus 1 is this is the group, and matrix A belongs to Gn and R such that A transpose of A. I mean, roughly just speaking, A preserves the Lorentz inner product. So A and -1 and then plus 1. This matrix is called Lorentz matrix. And this again -1, -1 plus 1. This form implies A preserves the inner product, that is Lorentz product. Lorentz product. And this is a typical. I think this is a very easy to see. Like n equal 2 in our case, then O11. This is an identity component. O11 in this case has 4 components. 1, 2, 3, 4. These 4 components. And the identity component is like, as you know that, cos theta, sinh theta, and sinh theta, cos theta. Not like O2. Minus doesn't come out. So, therefore, this is non-compact and isomorphic to R, hyperbola. And 4 component means preserving all component is this identity component, and then preserving this and then change this is 1 component, and also preserve this and then change this, interchange this is another component. And then this change is another component. So if we usually write down, maybe I should write down like that. O11 is identity component. The next is interchange -1, and then O11. Composite of this matrix. So this is not group. Next is O11 interchange 1 minus 1. And finally -1 interchange both in this kind of 4 components. But 4 components, but only group is still crime bottle, that is G2. So now the affine case. Of course, this is a special case of affine flat manifold. And next is compact complete. Next is affine flat manifold. I put complete always. Complete affine flat manifold is again T2 or K, but differ, not affine. Differ to T2 over K. T2 over K. So even dimension 2, let me mention this differ means if you want to insist affinely diffeomorphic, then you have to classify affine flat structures on T2. And these two are like Riemannian flat structure, also Lorentz flat structure is unique, just one. So difference is only conjugate, that is affinely conjugate. But in this case, T2 has several affine flat structures, complete affine flat structure. Then So this given complete affinely flat manifold, then it is affinely equivalent to 1 of T2 with complete affine flat structure. So I just mentioned that the classification of all of the complete affine flat structures on T2. So just say differ. So this is nothing said. Just say that the affine flat is as a manifold is T and K. Compact affine structure is many. This is the meaning of differ. Okay, then here it's now here the rest of time is I explain the dimension 3. So the okay. So dimension 3, first I consider in this way. In general, suppose in this way, suppose there, suppose maybe general. Proper here is say definition 4. Proper transitive. There is also simply transitive, but I introduce proper transitive E group action. E group G, which is G in general. In our case, in general, this definition, of course, you can in general, but we restrict G from the beginning. G belong to affine group, affine D group, okay, and this, and let's see. No, it's okay. Proper transit regroup is a definition is G belong to F_Rn and stabilizer is compact because just I said previously proper Gx is compact and transitive means it's compact for any point Rn. Okay, and orbit Gx is transitive means in this case is Rn. Okay. These two cases. Simply transitive is Gx is oh, I forgot important definition. G acts proper. So the G acts properly on Rn. Yeah, this is enough. Then G acts properly, so stabilizer is compact by definition. Yeah. Maybe this is not necessary. And but this transitive is so orbit is I don't know why some point P. Orbit is Rn itself. Simply transitive is orbit. Simply transitive is the definition is orbit is Rn, and the Gx stabilizer is trivial. That is free, acting free. So simply transitive is transitive and also G act free. This is the difference is G act properly. So not necessarily Gx is trivial, but this is the definition. Okay. Now let's consider, suppose G acts in this properly G acts properly proper transitive. G acts proper transitive on Rn. So G is now the affine group, and also in our notation, G acts properly proper transitively on Rn. Then what happened? So now we decide G, the form of G. Okay. So first of all, that's a general fact. General fact, that is G is a so-called decomposition, so-called Levy decomposition. General result, Levy decomposition. Levy decomposition. Decomposition. That is, G is, in my notation, R dot S. Here, R is generally group, probably, no, not probably. Suppose G has finite component, so you can assume G is just connected group in any case. Okay, now then G has the form R dot S, and R is the maximal normal connected solvable Lie group. And it is called radical, solvable radical. And S is a semi-simple Lie group. Semi-simple Lie group. And this dot means intersection. So R is normal subgroup, and S is complementary semi-simple group, and the intersection is in general, this is totally disconnected group. Totally disconnected. Sometimes it becomes discrete, but anyway, in general, this is totally disconnected central subgroup. Center. This intersection belongs to the center of G. Commutes every element of G. Okay? This is the totally disconnected central subgroup. This is the first step. Okay. Now then, now let's look at S is compact. Okay. The reason is G act properly transitive and belong to the affine action, proper transitive affine action. And then, first of all, let's look at S. Let's see. yeah, let's look at this. This is a very well known result. This belongs to the because this is a subgroup of G, that is G belongs to this one, so this belongs to Rn, which is Rn and GL and R. Okay, so this element is, you can write down translation A. My notation, this is a translation A and general linear group A. So this element S has a form A and A. And then this embed into one more up. I mean, like this A1, A0, 0, 0, 0. Belonging to one dimension up and plus 1 R. Okay. Then, of course, GLN plus 1 R acts as Rn plus 1, just as a linearly. Then here is the point: is S is also by this embedding or by this identification, S preserves X and X preserves R and Z. This vector is column vector R and Z. By this notation, this is ARN and so preserves RN Z. So I put this say B. So here you know that this technique. S is semi-simple. So semi-simple D group is completely reducible. That is, S preserves S invariant. S leaves this V invariant. Then S leaves the complementary V's in dimension. So complementary one-dimensional subspace. G preserves one-dimensional subspace, that is one-dimensional vector space line L, complementary to B. No, I just want to say I write down S preserves V and complementary vector space L, one dimension. Then, yeah, here like that. There is a picture. This picture is not necessarily there is a picture, but Auslander's argument also Milner's argument. Yes. Now, V is this one. Okay. And because of S is affine action, so S also preserves, like S is x1 go to ax plus a and 1. Yeah. So S preserves Rn and 1. This affine space is lying here. Okay. So I said, because S is semi-simple, completely reducible, so if S preserves V, then preserves also one-dimensional complementary vector space one dimension here, starting from here, one dimension L. Then this one dimension L is, of course, intersect with this affine space Rn1 here. Preserving this S action preserves here this line and also preserve this affine space. The intersection with this one and this is just one point here, unique point here. So S fixes P like that. P is this point. P is so like x1 something. So this notation actually, if you write user affine action, then element SA preserves AA x no is x no. So this S fixes x0. Okay. Therefore, therefore our assumption is S G act proper. So if this means at this point x0 stabilizer is whole space, whole group S. Every element AS leaves this point, leaves fixed this point. So S x0 is S. And by properness of G, S is stabilizer is compact by properness. So S is compact. Say kappa. Now then we have the following things. So far, G is in general R and S becomes compact coupler. Then let's consider R, this radical R. Radical R in general by Jacobson's result or from the Jacobson book. R is there is R mode dot similar product T. This is R has simply connected in general solvable group D group. This has simply connected solvable group R0, which is characteristic. This comes from the real algebra, okay, but I just translating the D group. Then there is in general R, then there is a simply connected solvable D group subgroup such that characteristic in R, that is given automorphism of R, which preserve automorphism preserves R0. And this is T is maximal torus. Solvable group, so maximal compact group is always torus. So this is, and then this is maximal torus. T is maximal torus. Then from this, then we have this decomposition R0 dot the product of K. K is the T torus and kappa, semi-simple group. This decomposition. Okay. Let's see. Okay. Then using this maybe give one proposition anyway. So maybe you might think that why affine action semi-simple group doesn't come out, non-compact semi-simple group doesn't come out, is because of this reason. Semi-simple completely reducible and affine action has a fixed point. And if you consider propaction, then fixed point is always compact. So the maybe propaction here. Suppose if I knew maybe unimodular is not so maybe unfamiliar, but unimodular group G contained in F Rn acts properly, then G is we have seen this G is similar product of simply connected solvable group, similar product of maximal compact group K. Okay. And then moreover, if G acts transitively, moreover transitively, so this splitting is unimodular. This splitting is if G acts properly, then this comes out. Okay. Moreover, if G acts transitively, that is G, some point GP is Rn, then if R no point, this subgroup is transitive. Maybe you can see this K is compact, so impossible, only R is there. So let me finish to prove this proposition. We have already shown this this result until here. Semi-simple group action, affine action. The only thing is RP no P is Rn.
Yeah, so why are you using the same notation K or T?
This is sorry, this is kappa. Small kappa. And I show this one. Yeah, of course, GP is Rn. What I said, this is R no is Rn. So let's consider the fibrillation. Okay. Rn act on G. So here is a considered fibrin like that. Okay. I don't mention so far unimodular, this meaning. But in this proof, I mean unimodular is there exists gamma in G, discrete, uniform. So there exists a discrete uniform subgroup, gamma, any whatever gamma exists. Then if gamma satisfy this condition, then G is called unimodular. So unimodular is used in this. So let's consider the vibration like that. G divided by any fixed point Gx stabilizer. And then this go to start Gx is stabilizer. Then this is by profoundness, this is compact. So compact so belong to maximal compact K up to conjugate. Profoundness, any stabilizer belong to the maximal compact K up to conjugate. So we have this vibration, homogeneous space, and fiber is so this one, so K over Gx. This vibration. Okay, so what we want to show that this is trivial. This is equal. The reason is like that. I think only this one that you cannot show. This, you need the unimodularity. So what we proved is like that. First of all, this is orbit, so Gx. And our assumption is if G acts transitively, so this is Rm. Okay. So it's okay. And this is because we have this one, this form. The G over K is R0, decoherent to R0. If R0 is not necessary, if not this R0 is not necessarily simply connected, then usually this happens. As you write so that G over K is equal to R no over R no over K. Okay, this is the usual state because of this. But R simply connected R0 is, in fact, this is contracted, deformed to some vector space K as a solvability group. Therefore, no, this is intersection is K, so this is compact. Compact group doesn't exist in RK, R0. So this must be, this is trivial. So this one happens. Now, because we suppose that gamma exists, therefore we consider in this way. Here's a projection. So what the next is because so far this is fiber, usual homogeneous space of fibrine, and if this dimension is same, then this is becomes covering because dimension is same, and this is simply connected. Then this is trivial covering. So step is fibrine becomes covering, and so simply connected. So this is trivial, and the reason is first of all, I need here a little bit technical things, that is cohomological dimension, okay? Like that. Since R0 is contractible, as I said, then R0 divided by, here, it's gamma divided by GK. This is gamma divided by G acton, K acton on right on G and left on gamma. So G double coset space G gamma G slash GK. Okay. This is R. So and then I switch. This is this notation usually. Then, because R is contractible, so this is a spherical manifold. A spherical manifold. Universal cover is compact. And because gamma is discrete uniform, that is, G of gamma is compact. So, and then compact by K is also compact. So this is compact. So this R no gamma is compact aspherical manifold. Then by the cohomology group theory, cohomological dimension, that is Hn of R0 gamma before interval, then this is not zero. So in this is algebraically this means cohomological dimension gamma is dimension n. So we have already Rn upton gamma as affine D. This is contractive. This is also compact affine flat manifold, and this is a spherical. So, and this is by definition this is compact. So dimension Rn. Oh, I'm sorry. This is dimension of those. Oh, sorry. I don't mention R, why I said N. But this N should be the dimension of this dimension of R0. Anyway, what I want to say, from this cohomological dimension with compactness, cohomological dimension of gamma is equal to dimension of total space of R0. And of course, this also same thing. The dimension Rn is equal to cohomological dimension gamma. That's compact spherical. So that is both this dimension Rn and this R0 is same dimension cohomological gamma, same as cohomological gamma. That is anyway. This is this also denoted R now n. So this fiber becomes same dimension. So this is the fiber is disconnected. Fiber is finite, but this is simply connected. Covering theory said this is trivial. That is. Then we have shown that. So final step is therefore. K becomes Gx. This is trivial. So, final step is final step is as follows. Rn is by transitivity. Rn is equal to Gp, say Gx. And this is we have shown. Where we have shown Gx, and this is equal to trivial. This is equal to Gk. This Gk is no. So this is P. Orbital R no is equal to. So it's different. So this and this is equal. This is by cohomological dimension. This is equal. So implies R no P is half n. Okay, I'm not using the compactness. I use only compactness in K. And the other argument is the spherical and cohomological dimension. This is a bit technical stuff. But, so the conclusion is so far finished, and conclusion is we in general we decided if the unimodular if the G act affinely as transitive also proper, then the group becomes G group becomes this one. Then one good thing is this is so-called amenable D group. Amenable D group. Amenable D group is in this case, because D group, amenable D group means extension of R0 biocompact group. And by Milner's theorem, in this case, any gamma, discrete subgroup gamma in this amenable group is virtually solvable, recycling. This is Milner's paper in 1978 or something. So, finally, how to apply this 3 dimension. It's already, if in any dimension, if there is such a G, then conclusion is affine group, fundamental group gamma becomes virtually solvable. So, the conjecture is true, is solved. So the point is how to find this. If you can find this, then you prove the conjecture, Ausländer Milner conjecture. So this is difficult. But in a dimension of 3, then, of course in general dimension, but there is a so-called algebraic argument. This is completely algebraic. This is called algebraic. This is algebraic group, but of course this has a D group structure. So the dimension is of 3 is R3 and this group GL 3R. So not so big. Then finally you can decide this group. From this group you can find the in fact G, this G. From this you can find the proper group G, which gamma is contained here. Okay. So from this transitivity is not necessary. If we prove this one without assumption of transitivity, just proper action then becomes like this. Therefore, from this already gamma is virtually solvable. Ausländer Milner conjecture is proved. So you don't worry about the transitivity, but in dimension 3, considering the algebraic how, then from this you can find the proper group G. Yeah. And so the gamma is virtually solvable. So to show the gamma, fundamental group gamma is virtually solvable is equivalent to find the such a proper affine group containing gamma as a discrete subgroup. So